So good morning once again. Um, so today we're going to take a quick look at how Clang modules work and hopefully get a good or at least better understanding of how they fit into the whole build process. So I'm at Giddins everywhere on the internet, and you've probably seen my name before in connection with a few open source projects. I recently joined the brand new mobile developer experience team at Square, where it's my job to keep all of our iOS developers happy and productive. So before modules, we had and still have header files in C. And in its related languages, headers are used to share interfaces between multiple different source files. So you declare functions, classes, and such in a header, and any implementation file that imported that header would be able to see the declaration. So in C, you gain access to the contents of a header with a #include directive. Without the #include in this main.c file, you wouldn't be able to call the printMyName function in a modern version of C anyways, since the declaration wouldn't be visible. C in this way is kind of a single file language. So this is what the compiler would actually see when it goes to compile main.c. That's because #include is a very literal directive. The C preprocessor will go and find the cool function.h header in your header search paths and then paste the contents of that header where the include directive is located. This leads to a few problems, especially when macros are involved, because depending on the order in which headers were included into each other, the C code the compiler actually sees can be different. Another problem is that you can end up with the same declarations twice, and the compiler doesn't like that very much. What's the value of the magic number here? What would happen if you had conflicting function declarations? It's a mess. So in C, we use this wonderful pattern of include guards to get around this problem. Things are slightly better in Objective-C because it introduced the #import directive. #import gets rid of the need for those include guards because the compiler keeps track for each .m file that it's compiling, what it has included, and it won't include the imported file a second time. So now enter module maps. The idea behind modules is that the compiler wants a more semantic understanding of what is being imported. Instead of pasting in text from headers, modules allow the compiler to tokenize and parse headers once and directly give access to the semantic content inside of them. They also replace what are called precompiled headers, or .pch files, which are a major reason why we have to run clean builds so frequently. So Clang modules are declared via a .module map file that tells the compiler what headers are a part of the module, how the module is structured in terms of its submodules, what the module depends on, and any special treatment the headers in the module need. Once your module has a module map, any #import or #include of a header from the module will be transparently translated into an import of the module rather than the C-style textual header inclusion. So this is the standard module map that you're probably used to seeing Xcode generate for you when you build a .framework. So let's step through it line by line, and then we can talk about some of the more complicated parts of how they actually work. So here, the module useful framework bit means we're declaring a module named, guess what, useful framework, And the framework modifier means the module is represented on disk by a .framework bundle. The header declaration is at the heart of the .module map file. It tells Clang what headers are a part of the module. This particular header is what's called an umbrella header, which is responsible for importing all of the other public headers in the module. The export star declaration means that every header that's imported by importing the umbrella header, including those that are imported transitively, should also be exported as a part of Useful Framework's interface. Finally, the module star export star declaration makes it possible for a file to import Useful Framework .framework class if there is a framework class .h header. This can make it more clear what part of a module your file is depending upon. So now we have our simple module map, and we can import our Useful Framework in both Swift and Objective-C code. That wasn't so hard, right? Okay, there's a catch. Of course there's a catch. I wouldn't be talking about it if there wasn't something more interesting to them. So let me start by saying that my frustrations come from trying to get Swift static libraries working in CocoaPods over the past couple of weeks. It's been difficult, mostly because it seems modules were designed with frameworks and possibly system headers in mind, with user-made libraries kind of being an afterthought. So this is just a small selection of the more complicated features and pain points that I've run into with Clang modules along the way. The list is by no means exhaustive. Umbrella directories, explicit submodules, private headers, textual headers, lots more features. There's automatic module map discovery, relative paths in module map files. So let's start from the top. The umbrella directory can be used when you don't feel like writing out an umbrella header that contains all of your public headers. Any headers found in that directory will be considered a part of your module, as if you had given them an explicit header declaration. CocoaPods should probably be passing your public headers directory instead of making a custom umbrella header. If anyone is interested in making that change, pull requests are welcome. Explicit submodules, don't worry, these aren't quite as bad as Git submodules. They allow you to export headers as a part of your module without having them exposed by default. This is useful if there's some semi-private functionality a consumer might need access to, but that isn't supposed to be a part of your module's main interface. A header with the private specifier is a part of the module, but cannot be imported from a different module. I tried adding them to the module maps CocoaPods generates once, but we had to revert that, and I can't remember why. Because headers and modules are pre-parsed, macros from different sets of headers are unable to interact with each other. This is actually one of the big selling points of modules. But if you need that little bit of nostalgia from C, you can declare a header as being textual, and including it will be treated the way includes used to work, simple textual inclusion. This is useful if you want a macro defined in your file, like ndebug, to be able to change how macros like assert defined in the header behave. Modules can also specify certain features that the compiler needs to support in order for the module to be imported, such as Objective-C or certain versions of C or C++. This can be used to automatically hide submodules that require certain language or other runtime features. So you can safely include, for example, C++ code in a module that should also be importable from a regular C file. The conflict declaration allows a module to say that it is completely incompatible with another module. In this case, if you import useful framework in the same file as pointless framework, the compiler will give you a warning about the conflict that will even include the message given in the module map. When Clang encounters a module.modulemap file in any directory in your header search paths, it will go ahead and automatically parse that module map and treat any headers that it covers as being a part of the module. That doesn't happen if you name the file something else, like baking.modulemap, and pass it explicitly to the compiler with the -fmodule-map file equals flag. I've saved my biggest complaint for last, and it's this. It's the only part of modules that I've yet to find a good way to work around. So any path in a module map file is treated as being relative to the directory that module map file is stored on disk. There is no way to tell Clang, either via the module map itself or via compiler flags, that paths should be resolved relative to some other directory. This means that your module either needs to point to absolute paths, as is the case with most system modules, or it needs to live in the same directory as the headers it represents. This caused a lot of frustration for CocoaPods, as we want any custom module map declared in the pod spec to work with headers stored in an arbitrary directory structure. Unfortunately, that simply doesn't work. Clang also seems to have special support for the headers and private headers directories found in framework bundles. I'm not 100% sure yet, but I think that special logic only applies to module maps found within a framework. So I know this is the part you've all been waiting to hear about. We are at a Swift conference. So Clang modules also provide a way for Swift code to be able to import Objective-C headers. They're the reason that, for example, import foundation statements work in Swift. Of course, the other way is to import headers via a bridging header. Now, you might be thinking that modules are all about headers, and your favorite thing about Swift is that it got rid of headers. So how do Swift and modules have anything to do with each other? By default, the compiler will generate an Objective-C interface for all of your Swift code that is marked @obc and public. You can see these generated module name -swift.h files in the headers directory of any framework built by Xcode that contains Swift. You can also manually pass the -emitobc header flag to the Swift compiler to force it to generate the header. Additionally, Swift compiler knows how to interpret binary Swift module files, and we'll treat them as being the same module as headers in a module map for the module with the same name. This is how you're able to have frameworks that contain both Swift and Objective-C, even though you can't use bridging headers for frameworks or for libraries. So this is the process for mixed Objective-C and Swift frameworks. Compiler compiles all the .swift files. It generates that module name .swift.h file in the now empty .framework bundle. It will extend the existing module map with a .swift submodule, and then it will compile the .m files. So these extended module maps are created automatically by Xcode when you are building a framework that contains Swift. They only reference a single header, the generated interface for the Swift code, but they make it possible for an obj at import of the module to import both the headers described in the module map, so the Objective-C interfaces, as well as your @obj Swift declarations. If, for some reason, your Objective-C code needs to be able to import Swift, or your Swift code imports Objective-C, all within the same module, Xcode can make that work transparently because the common factor for importing code is module. This is possible because both compilers know which module is being built, and Swift code being compiled before Objective-C ensures the generated Swift interface is in the right place. So these are the magic compiler flags that tell the Swift compiler that you're building a module that is a mix of Objective-C and Swift. It is passed automatically when building a dynamic framework in Xcode, but you need to specify it manually when building a static library. The flags basically cause the Swift compiler to import the module it finds with the same name as the module it is already compiling. So since so much of my recent experience with modules has come from implementing Swift static library support in CocoaPods, I think it is only fair that I link you to the pull request that contains all of the details. Be warned, it's not pretty, but it works. So after hearing all this, I suppose it's time for me to give my opinion on Clang modules. Do I think they're a long-term solution to the problem of importing an interface? Well, modules, at least from Clang's perspective, are still tied to the usage of headers for importing interfaces. And headers are starting to feel like a very old concept. None of the modern languages have them. Swift has also introduced its own binary module format, but it's not yet stable, meaning it needs to be rebuilt for each new version of the Swift compiler. And even after all this research, I find the actual implementation of modules to be confusing. And I've spent time researching them. There are so many different options, and even then it's hard to get the build system set up to support modules unless your project is set up in a very normal way. And that's a real shame, since modules do represent such an improvement over the status quo in C. If, for some reason, you want to learn more about Clang modules, here are some of the resources that I've found. I can't promise that they will be helpful. First is Clang's documentation page on modules. Next is the Clang source. which I used to figure out why things weren't working as I expected them to work when the documentation wasn't as specific as I would have liked. If you would like to skip the learning and just find out how to generate module maps, I'd recommend looking at the generator we wrote for CocoaPods. And last but not least, there's, in my opinion, the best way to learn anything: trial and error. So thank you all so much for listening to me ramble for the past 20 minutes. Please come and ask me questions. I'm happy to talk about modules and how we're using them to power CocoaPod's new Swift static library support all day long. You can also ping me on Twitter at any time. Enjoy.